We are moving to the last headings of this chapters. This headings is about the performance assessment. From the previous lectures, we talked a lot about the engineering to make the CPU fast, how to balance the performance between the processor and other components in computers to make the whole system plenty fast, despite the disparity between their speed. In these headings, we are doing some evaluations how fast is a program in a quantitative manner. That means we will do some calculations to figure out items quantitatively. For example, this program it runs on a processor clock at 3 GHz. I can calculate how many seconds does it takes, and if we increase the clock to 3.2 GHz, or if we move that programs to a multi-core system, then how much faster does it execute? We then compare the speeded amount when we do some improvement at the system level, like increasing the clock speed, modifying the clock cycle per instructions of the CPU. At first, talking about the parameters to evaluate a processor hardware. For example, when the chip maker design a new chips or new processor, they must put it into evaluation in terms of the power consumptions, the performance, the cost, the size, security, reliabilities of the new chips or the new processor. The evaluations of each items will deeply depends on the environments that we put into considerations, and in our lectures we focus only on power consumptions and performance only. First, we talk about the processor power consumptions. When the chips or the processor works, it will consume an amount of supplying power. This power is summing up from the two constituents, the static and the active power. The static power consumptions or leakage power is caused by leakage currents that are present in any active circuit, independently of clock rates and usage scenarios. This static power is mainly determined by the type of transistors and process technologies. The reductions of the static power requires improvements of the low-level system designs. It is not in the focus of these chapters. About the active powers. Active powers or dynamic power is associated with the capacitance of the chips. Vitamin C in this formula. It is the capacitance of the chips. The operating voltage, V here. The working frequencies, F, and the activities or switchings of the chips. Here we have the activity factors. The capacitance will depend on the low-level designs of the chips or the chip areas. The voltage determines both static and dynamic powers. The higher the voltage, the higher the power consumptions. In particular, voltage may be significantly increased dynamic switching power. Because you can see here in the formulas, active powers will directly proportionate to the square of V. So if we increase V by a small amount, the power consumptions will be increased significantly. Reversely, reducing the voltage may cause performance reductions, but at a certain point, reducing the voltage may prevent the design from operating properly. The design operating frequency F is usually determined by the frequencies of the clocks operating in the designs. The faster the clocks runs, they increase the switching frequencies of the transistor, resulting in larger dynamic power consumptions. Reducing the clock frequencies to minimal level required to meet performance will result in power saving. Now we need to calculate the active power of processor. These processors can work at different voltage and frequency steps. Here, the working frequencies can range from 0.9 to 1.5. Increasing step is 0.1 voltage. Likewise, for the frequencies, this processor can operate at the lowest level is 1.8 GHz and the highest frequency is 3 GHz with increment step is 0.2 GHz. And we can describe the different levels of frequencies and voltage in this tables. Here start with 1.8 the frequency, and the next level is 2, next level is 2.2, and the last level is 3 GHz. In the same way, this is a voltage. The lowest level is 0.9 and the next level is 1. Next one is 1.1, 1.2, 1.3, and the last level is 1.5 volt. Suppose the power consumptions measure equal to 30 watts at 1 volt 2 gigahertz. That means at this point the CPU consumes 30 watts. Now the question are, what is P for the most power efficient settings? That is the power that the CPU will consume at this level, the most power efficient settings. And what is the P for the highest performance setting? That means at this level, the CPU will work at the frequencies of 3 GHz and the voltage is 1.5 volt. Okay, now we will calculate together on this board. From the formula on the left, we have P equal to C capacitance, V power 2, F and activity factors. From the initial values, we have the CPU when work at V equal to 1 volt, F equal to 2 GHz, 30 watt. From these formulas, we can calculate C times alpha equal to P divided by V power 2 times F. Now we put the values of P, V and F into the formulas. C times activity factors equal to 15. Now we calculate the power consumptions as the lowest settings, that means this point, equal to, use the calculators, we have the result is, this is the wattage at the most power efficient settings. Now we calculate the power consumptions at this level. P for the most highest performance equal to, so the difference between the power consumptions at the most highest performance and the most power efficient is quite large, right? From 20, around 20 to 100, that means 5 times higher. Okay, now we'll talk about clock speed and cycle per instructions. About the system clock. You know, the chips or the digital circuit in general, our computers is a digital circuit in which we have the CPUs, the memories, the IOs, and many other components around. To make the digital circuit work, it will need a signal like this. We call this is the clock. This signal, when fed into the circuit, it will make all the elements in the circuit work at the same time, right? And normally the circuit elements will work at this moment, at the up edge of the signal. Okay, if you study the basic electronics, learns about this. This time durations is the clock cycle, and the numbers of clock cycles in 1 second we call the frequency. That means the clock cycle is equal to reciprocal of the frequency. For example, we say this CPU works at 3 gigahertz. That means there are 3 billions of clock cycles in 1 second. It indicates how fast, how responsive your system. The higher the frequency, the faster your system. Okay, the system clocks will govern the operations performed by a processor, such as fetching an instructions, decoding the instructions, and performing an arithmetic operations, and so on. The executions of instructions involve fetching the expressions from the memory, decoding the various portions of the instructions, loading, storing data, and performing arithmetics and logical operations. Most instructions on the most processor require multiple clock cycles to complete. That means for the CPU to complete an instructions, it needs some instruction cycle. And the cycle per instructions, in abbreviations CPI, is the numbers of clock cycle that the processor must take to complete an instructions. Now we will do some calculations on the time that the programs will take to finish a programs. We call this is the iron law of performance. The time to execute a programs or a CPU time is equal to the number of instructions that need to be executed times the instructions, the cycle per instructions, or times the CPI, then times with the clock cycle time. This formula is obvious. Let's take the first quiz. A program executes 3 billion instructions in a processor. That means IC equal to 3. The processor spent 2 cycles. The CPI equal to 2. The frequency, now we use the formulas. And now we put the numbers here. That means this programs, when runs on this CPUs at 3 gigahertz, will take up 2 seconds to finish. But you can see that this is not very practical because on a CPU there are many times instruction time, and each instructions will take different clock cycle to finish an instructions. This is another quiz. A program contains 50 billion instructions, whose composition is 10 billion branch instructions, and each one will take us 4 cycles to finish. 15 billion load instructions, which take up 2 cycles to finish. Then 5 billion of store instructions, and each instructions will take up 3 cycles to finish. And the last one is 20 billions of integer time instructions, and each will take up 1 cycle. Now we need to evaluate the execution time for these programs if the system is clocked as 4 gigahertz. We have in our last formula, the formula is, now we need to modify this formula because for individual instructions we have different CPIs, must be modified to. For the branch instructions we have 10 billion, so this is 10 power 9 times the CPIs of this instruction is 4, right? Plus 15 billions of load instructions. This is 15 billions times 2, which is the CPIs of these instructions. Then 5 billions, 20 billions times the CPI, right? And this then times 1 over 4 gigahertz. That means 4. Simplify this. This will equal to, this is the time that the CPU takes to finish the 50 billion instructions of these programs.